So thank you all for coming right in after your lunchtime. You're in the Research and Green Stormwater Infrastructure track. This is Infiltration Feasibility, Assessment to Successful Infiltration Design and Performance. And our speaker is Jennifer Saltonstall today from Associated Earth Sciences. She will be our only speaker, and she'll do both parts of the presentation. The other speaker is not here today. The abstract for this presentation is we're presenting key findings for successful subsurface geologic characterization, estimating design infiltration rates for a range of project types. She's going to review infiltration feasibility assessment fundamentals and design concepts, the pilot infiltration test procedure, and grain size correlation method, and discuss the geology of Puget Sound, and describe how water is moving through the subsurface in different hydrogeologic settings. The work is based on 20 years of infiltration studies as part of land use application and retrofit projects, and the recent work conducted as part of the Bioretention Hydrologic Performance Study funded by SAM. The presentation will provide guidance for municipal permit reviewers on what is contained in a geotechnical report and provide design professionals with key lessons learned to improve infiltration design. Thank you very much for being here. Here's Jennifer.
All right, thanks for joining me after lunch for a pretty full, meaty talk here. So 20 years of my experience, and then Curtis, who's not here, has another 10 beyond me. So we've done a lot of infiltration in Puget Sound in support of land use applications. Most of our early work was for residential, some of the largest residential construction projects in our area, Snoqualmie Ridge 2, Redmond Ridge 2, all the big master plan developments, and then a lot of school construction support, so stormwater management for school construction. And then in the last 10 years, more municipal work, so stormwater retrofits and redesign projects, so a wide breadth of experience. We also are one of the geotechs who still does single family residential, so we've seen the small projects to the very large. Thank you for going through the abstract. That just covers what we're going to talk about today. So I'll just keep on going because there's a lot in there that I want to cover. So as a geotech, I'm a hydrogeologist, work with geotech engineers. Hydrogeologic characterization, geologic characterization, it's, from our perspective, the #1 part of the stormwater plan. A lot of this conference has been on the water quality components. This is all about flow control. So when we want that water to soak in the ground for flow control, when it's infiltration, that's where the subsurface characterization is very important. Think about the ground as your underground pipes. So the pore spaces between grains, the layers of materials, that's your pipes. And you need to understand how they're deposited to understand their flow carrying capacity. So these 3 bullets, thickness, lateral extent, where's the perching layers in the water table, and then that permeability in the vertical direction, those will be themes we'll touch on throughout. So who knows who Carl Terzaghi is? Geotech engineer, father of geotechnical engineering. So this was an engineer who recognized that how sediments are deposited are key to predicting their behavior between widely spaced boreholes or widely spaced tests. It's really hard to predict the subsurface because you can't see it. You get these little tiny windows into the subsurface. How do you predict conditions between those 2 locations? It comes back to understanding the geology. How were the sediments deposited? So this is a Puget Sound centric talk, but the concepts here apply statewide. But Puget Sound in particular, we had the glaciers come down, over 6 times in the last 2 million years, and they left behind a very complicated subsurface story. So I want to just lightly touch on this because there's 2 key units that the ice sheet left behind. Derek Booth, a local yokel, worked for King County, went off and is a worldwide expert now on stormwater, but he worked at the county in the 80s and then UW in the 90s, and spent a lot of time characterizing geology and groundwater flow. And so recommend that everybody read his paper. It's really good. And it forms some of the basis for the hydrology we see locally, and it helps understand how facilities will perform. So those two key units, glacial outwash and then glacial till, those will also be repeated here. So outwash is deposited from the ice sheet, from meltwater streams outwashing in front of the ice sheet. That's where outwash, the term, comes from. So sediments deposited in front of the ice sheet as it's moving south or as it's retreating north are water sorted. Why is that important? So when you sort sediment, you create layers, you create stratification. You've got zones with very little fines. The fines have been winnowed out by the action of the flowing water. There's also areas where you have still water and fines accumulate. And so it's a very heterogeneous, highly variable, laterally extensive unit, so the outwash. Advanced outwash is over-consolidated for the geotech engineers. It's been consolidated by the weight of the ice sheet. Recessional outwash, normally consolidated. It's loose to medium dense. Its geotech properties are different. Advanced outwash, since it's been compacted, all the pore spaces are smaller. There's less space to move water through it. The fine-grained layers are low permeability because when you compact something that's silty, you really seal off its permeability. Recessional outwash wasn't consolidated in the same way. So recessional outwash for the same grain size will have an order of magnitude higher permeability because the pore spaces are larger. And in general, outwash is a good place to put your infiltration facilities. It has a good permeability when it's not saturated. So on the flip side, glacial till. Glacial till is formed at the base of the ice sheet. As the ice sheet moves south, it is compacting and scraping and pulverizing. It's like a bulldozer. Glacial till is nature's concrete. It's hard pan. People do not like to dig fence post holes in glacial till. It's hard. It has a bimodal particle size distribution. That's the word of the day, bimodal. So the matrix is a silt to a silty fine sand, and it's been compacted. And you've got these larger particle sizes kind of floating in that matrix. In the stormwater manuals, glacial till is the recommended material to build earthen dams. Glacial till has a very low permeability in the unweathered condition. So that inch to inch and a half a month, that's what USGS has measured for recharge vertically through glacial till. So that's the geology. So when we do site characterization, the geotech comes out, does their work. The civil is doing work at the same time, and we need to be able to talk to each other. So civils do the drainage report, civil stormwater engineer, and they have a surface water model that uses soils to predict runoff. So the soils in glaciated terrain are less than, they're about less than 10,000 years old since the ice retreated. They're not the same as soils in the south. So our soils directly relate to the parent material. And so that parent material is typically your till or your outwash when you're not in a modern stream valley. So the ABCs of soils, the type A soils are outwash soils. So Everett, Indianola, Spanaway, those are all soils formed from the weathering of glacial outwash. And then your type C, for the stormwater model, type C looks at the Alderwood, Harstein, and Tokel as type C soils. Those are formed from the weathering of a glacial till soil. So this cartoon is our picture of water flow on a type C soil site or a glacial till site. Stormwater models are trying to mimic the pre-developed condition. So under the pre-developed condition, there was a thick weathered horizon on top of that glacial till. That weathered zone in a true forested condition prior to logging was probably 6 feet thick. And it was a sponge, nature's sponge. It was a really good place to store rainfall and slowly release it. It had a moderate permeability, and once water got in there, it could move laterally along the top of the unweathered till. And it provides the base flow to wetlands and those small headwater streams, intermittent in the winter, as the inner flow is releasing its water to those drainages. And then beneath that is the hard unweathered till, the nature's concrete. It perches groundwater. So that till, the hard unweathered till, if it had an infiltration rate on the order of a 1/4 inch an hour or a 1/10 of an inch an hour, we would not have any wetlands. They would just dry up. So it's really important to understand the weathered till horizon versus the unweathered till. Two very different permeabilities. So going back to the subsurface characterization, this is what I want to talk about today, is what to look for in your geotech report and your civil reports so that your site characterization is consistent between the two technical documents. So the goal of flow control is that it work, and that we don't have high runoff rates to our streams and to protect our salmon, but it's also because we want facilities that work. We don't want drainage complaints, and we don't want lawsuits on neighbor properties. And so when it doesn't work, it is no fun at all. So the upper cell, not selected for study. This was one of the facilities we looked at as part of the participation in the Stormwater Action Monitoring project. So we reviewed many built bioretention facilities across Puget Sound. This one was not selected for study because there was some trouble. The upper photo is the excavation for a bioretention cell that's going to be built. They excavated through the Alderwood and into the fresh, unweathered glacial till. The lower picture, they've placed the topsoil. The bioretention soil hasn't been planted yet, had a storm, and some problems started to appear. You can see these little divots on the side of the cell where that soil is starting to fail. And it has standing water in the bottom of it. And so a year later, there was trouble with it, and there was a stop work. All the soil is gone from the sidewalls. It's not draining. It's a really good detention facility. So in that sense, flow control is achieved, but it's not what anybody wanted to see. So where should this water have gone? It's when it gets high enough, it can access the weathered horizon. And then in the lower photo, this block wall is off to the side, and there's seepage at the base of the block wall, that lateral flow. So this is that picture again. So this is, just want to hammer this home, that the inner flow horizon, the weathered till, has a moderate permeability, but it's lateral. The vertical permeability, it hits that unweathered till, and it just isn't a measurable rate in how we want it to be for a stormwater control facility. So how should we estimate infiltration rates? We could spend a whole day talking about how the way infiltration rate estimates are provided has shifted over the years. Historically, there was a lot of literature from septic and agricultural purposes, low dosage applications, small diameter tests. For stormwater facilities, they're not representative, and there were some pretty impressive failures in the 80s and 90s, and that's why King County led the charge and came up with a better way, a more representative way of estimating infiltration. This is kind of some numbers that you can look at from left to right. The two tests on the left are the standpipe and the double ring. Nobody uses double ring anymore. That was used for landfill cover. Very low permeability stuff. Should not be used for stormwater runoff events. And the standpipe is, it's just a small diameter, and you can carry the water to the test. How is that going to replicate a storm when you're concentrating a lot of water in a flashy fashion? And then on the far right, you've got the large pit, just a different scale. A lot more water is put into the ground. You're stressing the system. The number you get is going to be more representative. So a couple of cartoons kind of trying to illustrate that concept of how much area you're affecting with the different types of tests. So this is just context for when you're looking at infiltration rates that are provided to you. Understand how much water was used. And then grain size. What about grain size? Grain size is a cheap way to estimate infiltration. That's why everybody wants to do it that way. And context is very important. So when you sieve a soil, you're homogenizing or averaging any sort of layering it might have had in its natural condition. And you know, I'm a data miser. So for the last 10 years or so, when the Massman formula came out, we started compiling pilot infiltration tests and grain size data, and just to see how it compared. And what we've seen over and over again is that it overestimates infiltration, the grain size-based formulas, when the soil is silty, or if it's gravel, it kind of falls apart. It's too coarse. And so you just got to use caution with grain size-based estimates. They should be heavily factored, and hopefully the soil is pretty homogeneous. Then you're being conservative. So for infiltration projects, this is what you want to see. You want to see a good description of the soil. Hopefully there's a geologic unit attached to it. Is it stratified or not? And is the rate measured vertical or horizontal or not discussed? Where's the water and where's the water going? A couple of photos here of stratification. These are both of advanced outwash, so a consolidated, over-consolidated material, and a lot of different permeability exposed in that cross-section. So who reviews geotech reports? There's a lot of variability. The standard of practice is highly variable, but in general, there's 3 types of reports that we produce as a geotech and that I see when I review other people's works. And it's a pretty basic, this is what we've got, this is what we think for feasibility. Then the next phase is, okay, we think we've got something that'll work. Here's our design information. And then there's the single family geotech reports. So 3 pretty different apples. In that first one, this is just kind of a list of 5 minutes. Okay, so this is what you should expect to see. Pretty basic stuff, maps, logs, generic description. What I want to spend time is what we should expect when we're actually doing an infiltration design. We're not trying to prove it doesn't work or it does work. We're actually trying to provide design information. So a key one is, what's the basis for the water level? Does the water move up and down, and where are you in the season? And then on the next slide here, did they put together a cross-section that shows how the unit extends? Is the unit thin and truncated against a rockery, or is it thick and extend for hundreds of feet? Those are 2 bookends that you want to know, because you're trying to understand where the water is going. You want a statement in the report about where the technical person thinks the water is going to go. For single family, you know, they're just different. It's smaller amounts of water. Single family infiltration, there's a lot of prescriptive sizing based on grain size, but the grain size basis is the USDA, not the Soil Conservation Service, but the Natural Resource Conservation Service textural triangle. And it works great. It's conservative for gravel, and it's conservative for medium to coarse sand, but it's not for the finer portions of the triangle. So just caution, caution, caution. And let's think about that. For another talk, it would be, why are we using septic-based design parameters for stormwater flows? Septic is based on low dosage, regular low dosage, and the drain field is just a bunch of infiltration trenches. When you think about it for stormwater, it would be wonderful to have a sanitary person compare the amount of water we're talking about for septic versus what we see from roof areas under storm. That would be really interesting. Going back to soils and geology, so the Everett soil series derived from the weathering of glacial outwash. Infiltration actually gets better the deeper you go when you get out of the weathered horizon, because it's generally less silty. The Alderwood, soils derived from the weathering of till, it's the inverse. By the time you get deep in the soil profile for Alderwood, the original soils Conservation Service documents, they're wonderful reads, and they know there's standing water there, and the vertical rate is nothing at depth in the hard unweathered till. So the last slide to think about when you're looking at those two pieces, the Geotech report and the storm report, look for disconnects. So if the Geotech report doesn't talk about the way they got the infiltration rate or the amount of water used for testing or where the water is going, then you should have a comment letter that says, give me some more information about the basis here. If the drainage report has a class type C soil for the runoff, but they've got the infiltration box checked, then that means we're putting water into the weathered horizon, and that means it's not moving vertically. And so there's a disconnect there that should be discussed. And then, is the grading plan removing the zone that was tested? So I don't know how many times I've seen tests done, and then to make terraced lots, you're just cutting and filling. And maybe they're filling where the facility is going, or they're making a 10-foot cut where they did the infiltration test. Just that basic cross-check is missed because people are in a hurry, and they're trying to get plans in to get that submittal date because they know it takes 3 months for review comments or whatever it does. Maybe more people are efficient. But there's just stuff gets missed. So those are things to look for on the review end. But when the infiltration rate is a small number, your review alarm bells should go up, and there should be a lot more questions about where that water is going and does it make sense. Safe overflow path, really important. And then in the end, who's in charge of making sure it's built right? Who's doing the construction observation? And is there a good conversation with the contractor about what this facility is for? It's not the TESC pond. It's the final built feature, and you don't want dirty water going in there. So I think I'm out of time, so I'll stop for questions.